Well, it's time. Welcome back, everyone. This will be our final class for the entire semester. Congratulations on getting through it all. Today, we're just continuing on reviewing through this document we have here. We're probably about halfway done, and whatever problem we don't finalize, I'll return to this and get the solutions fully posted after grading through on Friday. But just for the typical rundown of the announcements, the final quiz, number 12, is going to be due today. And we won't speak as much on the extra credit opportunities. We've talked about them before, but don't forget that there's a pretty massive extra credit opportunity for the final exam itself. You can get an extra credit on the course evaluation by just sending an email, quick message in Canvas that you've completed the evaluation. It's the pop-up that you see in Canvas. And that'll allow me to drop the lowest 2 homework assignments at WebAssign at the end of the semester. And if you're behind on any material, quizzes, WebAssign being the 2 major things, then Tuesday, May 7th, 11:59 p.m. is the last day for getting caught up. Other things to recall for the exam is for materials, don't forget to bring your calculator. You don't need to bring this. This is provided on the real exam. And as you're studying, I put down a lot of material. These are the same kind of versions 1 and 2 that you saw throughout the course, but now it's the entire course all in one spot. So they're rather large packets of information. You can use them to target particular sections that you want to brush up on the most. All quizzes are here. If you put all of your quizzes together, that's a decent sample final exam as well. And these are the blank exams that you took throughout the semester. Great way to use these documents is if you look into where your lowest exam score is, go take that exam again. Just print it out, put down a 75-minute timer, try to do those again, and that will give you extra practice on another run through of those. Aside from that, again, these are really long packets of information. My final exam, I'm not going to try to write as a strictly you're working for the entire 2 hours. It's going to be pretty similar to the problems you see here in terms of difficulty and length. So we're giving out quite a bit of hints as we're going through this. We'll continue to do so. But any last questions or comments whatsoever before we start? Okay, and again, just one more reminder for the in-person section, we'll just be here on Tuesday. This is a little bit later, 5:30 to 7:30 p.m. for the final exam. If there's any conflicts with that, just email me as soon as possible and I can make other kinds of arrangements. For the online section, schedule your exam as soon as possible with the instructions I've sent you. And if you're not sure where to find them, as usual, just send me a fast message, either Gmail or through Canvas, and I'll get back with you right away. But let's jump in. We left here before concluding our review on Tuesday. I mentioned there's going to be a problem like this one where logarithms are involved. This was kind of a heavier problem, a lot more going on. I'm not going to try to write as big of a problem on the real final exam, but this is still good for practice, so we did a harder one. First thing we did was we broke down this h of t function, I guess h to stand for hard. H of t got broken down to this after using all the properties of logarithms. But now that we're at this step, differentiation, the second part of the problem, should go pretty streamlined. So let's work through it. The derivative of h at t is first the derivative of the natural logarithm of x. This one's nice. Just a 1 over x. Here, it's the power rule, so we get just a 10. Here, it's a constant multiple rule, so 1/2 carries in and multiplies another derivative. This one's a chain rule, so we'll do it in 2 stages. Stage 1, here's the format for the derivative of any logarithm. 1 over the inputs, just like we did for that derivative here. But there's more going on inside that input, so we multiply by the derivative of whatever is in there. And usually people just put the derivative up into the numerator. But this is the strict step-by-step process. Then take 2x minus 11, copies in the denominator, and it also gets differentiated right in that spot. So much like this x went down to that position, that 2x minus 11 went down here. If you multiply that by the derivative of x, that's just multiplying by 1, no harm done. But here, We can't ignore it. The derivative of that is 2, so that does have to be there. So all we need to do is finalize this last derivative. Any questions on the first step? Okay, running through it, we now have the derivative of h at t, 1 over x plus 10 minus a half times 2x minus 11. And then the derivative of 2x minus 11 is a 2. It's multiplying a fraction, so it can go in the numerator. And then now it simplifies more. Sometimes it just keeps on going and going. That half and the 2 in the numerator simplify. So now it's a 1 over x plus 10 minus 1 over 2x minus 11. And this is a very good stopping point. Typically, when we're doing this kind of problem, the expectation is you're not going to find the least common denominator and add them together. If you did, it wouldn't hurt you. It would just be eating up time. So I would encourage you to stop at that stage. So again, that was a kind of a trickier problem. Expect something like this, but not as much going on. You'll break it apart, probably use the power rule, the quotient rule, product rule, and then differentiate what you have. Well, any questions at all, folks, on the conclusion here? Okay, after finalizing this one, we're out of chapter 3 entirely. We moved into chapter 4. We're looking into applications of the derivative. And here's one big application right away. Finding maximum or minimum values. This one's strictly about the local maximum, local minimum values. This one just says straight out, find them. So if you're dealing with a problem like this, very first thing we're going to do in a step-by-step guide to get these values is first just differentiate. The function's tricky. It's another chain rule problem, so we're practicing chain rule quite a bit in this section. Let's maybe rewrite it so we can expand it out a bit. F of x is e to the power of, I'll put in parentheses, x cubed minus 12x. This is not our first chain rule, but they're all tricky when it's an exponential, I feel like. So let's go carefully. The inner function is that whole thing. The outer function is base e exponential. So if we go to differentiate this through the chain rule, process would look like this. F prime of x, first, differentiate y equals e power of x. That's e to a power, so we write it like that. Then we chain on a new derivative, and let me scroll up for maybe just a touch, where we did the chain rule right up here. Really, it wasn't any too different. Instead of ln, we had e to a power. 2x minus 11 was inside here, but on this one, it's x cubed minus 12x. And that's why we throw in x cubed minus 12x here and here. And I did forget one thing. Don't forget you have to differentiate right at that spot. Let me highlight it for emphasis. So whether it's a natural logarithm, base e exponential, or anything else, the process is always the same. The inner function gets copied in 2 spots, differentiated in the second position. And that's a fast derivative, so we're actually almost done with this one. Let's differentiate it. F prime at x is now, I'm going to take this derivative but move it off to the left-hand side. That's going to be equal to, we'll still need parentheses, 3x squared minus 12 times e to the power. We can drop parentheses here. It was mainly to visualize the chain rule. X cubed minus 12x. Now, once we have that, step 2 is get the critical number. So step 1, just differentiate to whatever your function is. Let me scroll up just a touch. There we go. Here's the function, now differentiated. When it says get the critical number, all we're doing on the second step is solving the derivative of f at x set to 0. So if we're setting this to 0, all we're taking is that whole thing, 3x squared, minus 12 e to the power x cubed minus 12x. Set that whole thing to 0. Although this factors where the red dot is here, we are in a factored form. It's not factored completely, but that's a pretty good factorization. Let me put the multiplication symbol there to emphasize. So now if you have two factors multiplying, resulting in 0, the immediate implication is that one or the other is 0. So either 3x squared minus 12 is 0, or e to the power x cubed minus 12x is 0. This equation looks complicated, but we've run into this kind of situation before, multiple times in fact. Whenever you see this and it involves a base exponential set to 0, the idea is e to the power of a can't be 0. It doesn't matter what a is. It could be x cubed minus 12x, but it doesn't matter. There is no way to get a 0 on this whatsoever. It's strictly positive. So this has no solution, which is nice because that means we get to focus on just that right there. We've seen a lot of different methods for solving these kinds of things. We'll do another equation solving in the next problem. But if you have x squared just appearing in one term, let me fix my penmanship, then probably the easiest way to solve this is to isolate the x squared term. So let's rewrite it as 3x squared is 12. Divide by 3, so x squared is 4. Now be cautious here. It's a degree 2 polynomial, which means there could be at most 2 solutions. This one, in fact, has exactly 2 solutions. Take the square root of both sides, and x is plus or minus the square root of 4. I'll put the solution to the right. That means the solutions are x equals -2 or x equals +2. And you can check, square root of -2 or +2, you'll get a 4. So those two values are the critical numbers of our original function f. So that's step 2 in the process. First, differentiate. Next, set the derivative to 0 and solve. Just about every one of our methods in chapter 4, when it came to optimization, had this first 2-step process. Now for step 3, if we're looking for local maximum minimum values, we're also doing another thing. We're going to find the intervals increasing, then decreasing. That'll imply a maximum. If it goes from decreasing to increasing, that will imply a minimum. So here's step 3. Write down a number line. We're going to find intervals where it increases, decreases. This is not the final step, but this is the last big step. Take whatever your critical numbers happen to be. Another word for these are, in this context, cut points, because now we're cutting up the number line. One cut at the first critical number, -2, another cut at the second number, +2. That implies 3 different regions for the real number line. There's a far left region. We'll test the sign of f prime. A region of finite length from -2 to 2. And the far right region of infinite length. We put f prime on all 3 because we're going to analyze the sign of the derivative on all 3 intervals. So this takes us to the next step, the next segment of the process. Here we're going to use test points. Still considered to be step 3 altogether. But any questions at the moment with the analysis? Okay, as far as test points go, we just pick the most convenient value you can think of in any one of these 3 different regions. For this one, probably -3 is what's going to work out the best. If you say x is -3, what you're doing with that -3 is you're going up to the derivative here. So plug -3 inside, f prime at -3 is kind of a lot of stuff. Let's write this out. 3 times -3 squared minus 12 e to the power of -3 cubed minus 12 times -3. Geez. Well, you know there's a nice part about all of this, it didn't matter what was in the exponential because this is still in play. Any power is always positive. So whatever the sign is for this whole thing depends upon what's in the parentheses themselves. At this point, it's a great idea to grab a calculator, just figure out what the value is for what's in the parentheses. This is 3 by -3 squared minus 12. So that's a positive 15 altogether. That, even if you put it in your calculator painstakingly, it's still positive. So at that test point, our major conclusion is it's bigger than 0. So f prime is bigger than 0 here. If the derivative is increasing, it's telling you the direction the function is going. It's going up. So we'll say it's increasing here due to the positive derivative. So 1 down, 2 more to go, and we'll have the full analysis for where the function increases and decreases. And again, you don't have to work too hard here. Just plug it into the calculator. We do not need to know the specific value, just the sign. So rinse and repeat. The most convenient value in that interval is absolutely 0. You could pick 1, you could pick 1.9995, but we don't want to take too much time. Pick the most convenient value, set x to 0, go back up here, plug it in, f prime at 0, means you're plugging 0 into all these values. That's just going to be a -12. E to the power of 0 minus 0 effectively, that's just e power 0, which is 1. So this one, very fast to analyze, is absolutely negative. So back over here, less than 0. The derivative is negative. The function is going in the same direction, down, or decreasing for short. Then same idea with this one. Plug in, say, 3. So 3 is going into these values. F prime at 3 is going to be 3 times 3 squared minus 12 e to the power of 3 cubed minus 12 times 3. But if you look at that really, really close, there's no difference between line 3 and line 1 because -3 squared is equal to 3 squared. This is 9, that's 9 times 3 minus 12. Same exact values. You don't even need to put this in your calculator. But you know if you did, it would look like this. Same value, still positive. This value is absolutely positive as well. It didn't matter what numbers went in. So we have greater than 0 here, greater than 0, which means increasing on this region. And we nearly have the complete analysis. Last thing you might want to put down on paper, just to kind of make sure we get the right conclusion, is we never graphed the function, so this graph is not meant to be completely accurate. But if there was a y-axis and I were to try to plot the function, it went from increasing to decreasing around -2, so the curve would look like this. Right at -2, it would have a local maximum value. We want the second coordinate for the value, the output to the function. Likewise, around 2, it went from decreasing, horizontal tangent line, that's where the derivative is 0 per the critical number, to increasing, so the shape of the curve would look about like this. I don't know exactly what the height of the curve is. It could be above or below the x-axis, but that's the shape of the curve generically, which means we're ready for some conclusions. This would be the local max. Is f at -2. We just need to come up with a number. The local min is going to be f at +2. Just need the number. So that's what this number line is providing for us. So at this stage, we're just going back to the very original. We need to say that the local max is equal to f at -2, get a value for that, local min, equals f at +2, get a value out for that. So if it's -2, we're plugging it in right up here. You would get e to the power of -2 cubed minus 12 times -2. That's e to the power of -2 cubed is -8. -12 times -2 is 24. So that's e to the power 16. Really, really large number. Just for emphasis, here's our local maximum value. E power 16 is about 9 million, if I see those digits right. Yeah, about 9 million. So pretty large number out of nowhere. That'd be kind of annoying if we tried to find it with a graph because you're zooming out for a while. Then likewise, local min, we the original function because max and mins are about that function at the top. Take e to the power of +2 cubed minus 12 times 2. So that was just plugging 2 up here. That's going to be e power 8 minus 24. And 8 minus 24 is -16. So this function had some kind of odd symmetry about it. The maximum was e power +16, a gigantic number. And this one is minuscule, e to the power -16. Recall, no matter what, it's positive, but they had to use scientific notation to say how big it was. 1.12 to 10 power -7 in terms of order of magnitude. Pretty close to 0. But we did it, folks. That's the optimization on this one for local maximum, local minimum. Any questions or comments whatsoever getting through it? Okay, well, let's turn to the next example. This one's a pretty big wrap up of the things that we did in chapter 4. We have everything, critical numbers, intervals of increase, decrease, and local minimums, local maximums. This next one is going to be about an absolute maximum. So we've solved a problem similar to like this one before. I think we mentioned that possibly it could be on exam 3, but the rest of exam 3 has to be a lot shorter because it's a longer problem. My hint to you is you can expect something like this on the real final exam. Different kind of situation, different sort of numbers, but some kind of optimization problem along these lines. And one thing when I looked into this problem is the unit of meters is weird. This is going to be a gigantic storage container, which means the cost of materials is absurdly cheap. So this is one of those, it's just purely a math problem, not something that corresponds well to reality. I should have changed it to like inches or something like that. So weird dimensions, weird costs of the sides. But let's read through it to see just what's going on. A rectangular storage container with an open top is to have a volume of 12 cubic meters, which is, again, gigantic. That might be used for something like a huge bin for mulch or a big trough for farming fish, something along those lines. The length of the base is 3 times the width of this rectangular storage container. When it says open top, the interpretation is no top whatsoever. The base costs $8 per square meter. It should have been like 800 or something like that. Material for the sides is $5 per square meter. And we want to find out the cost of materials for the cheapest such container. In other words, what should the length be that's going to give us the cheapest container, which will imply what the height and the width have to be as well. It says, do not round intermediate computations, round the minimum cost to nearest cent. So here's where we're going to start. We have a rectangular storage container, the base 3 times the width. Although you don't have to draw anything, anything you do draw kind of helps our mind organize all the information. And if you're not very artistic, neither am I. Here's the strategy. I think we're going to reuse the same exact strategy from when we did this in class. Draw 2 squares, basically. It doesn't have to be squares. They can be rectangles, but that's what I'm going to go with on this. Here's your 2 squares. Kind of offset them in a bit. Then start drawing line segments, joining vertex to vertex on the square. If you're really good with shading, you can include some shading. I'll do a little dashed line to say the front face is blocking until we go beyond that edge. And there's a little bit more you could work on this to make this look. You're not required to do so, but since this is for our own visualization, let me try to make it look a little bit better. That part is going to be blocked by the right side of the face. So here's our rectangular storage container. Again, it's fiction, but we can still optimize it to see what's going on. Maybe the material for the sides is like a tarp, but that's why it's so cheap. Now we've got a rectangle down. It says the length of the base is 3 times the width. So from that information, I would make this be the length because that's the longer side. That be the width. This be the height. Next bit of information is that the volume is 12 meters cubed. But volume is just length times width times height. So volume is going to be equal to just this quantity. Much like area is length times width, I'm not going to go beyond any kind of formula like this. So expect to use this formula on the real final exam for volume. Just multiply all the dimensions together. So now we know that 12 cubic meters is length times width times height. This doesn't give us much to use with calculus because we still haven't put down a variable we can work with. I mean, that's 3 variables. Here's our next thing we can do. Go back to this line where it said the length of the base. Put in an X, right, when it said length of the base. So there's that length. 3 times the width. That would mean L is 3 times W, or 3X. So now we have 2 variables down, both involving X. H is not related to the length or the width, so we need a third variable. We can call it Y. So that's the setup so far. Now, if we go back to the volume equation, I'll drop the unit for the moment so we can focus more on the algebra. This is saying 12 is equal to length, that's a 3x, times width, that's x as well, times height, this is here's the variable y. So that means 12 is equal to 3x squared y. And let's make kind of a clean approach on this. When we did optimization and we built functions, oftentimes we need to get into one variable, and y variable is the odd one out. It pays to do this right here. Let's just solve for y right at this step. We can divide by 3x squared and say y equals 12 over 3x squared. Simplify that. 3 goes into 12 4 times. And this is slightly more convenient if we change the base to the numerator's position and write it as power -2. So we've got a nice setup so far. From this diagram, the constraint that volume is 12 cubic meters, we can say that the y variable is 4 times x power -2. It's a decent algebra problem already. And I'm giving a lot of partial credit for this kind of problem. So any work you do in the right direction, even if you make a mistake here, just keep on going. If you're doing the right next steps, then you still get a lot of partial credit. And even if we got the wrong critical number, if we have a problem with our function, if you just work function in part B, come up with the right conclusion in your information, you would get full credit on part B. So just continue going through it. Next thing we need to analyze are the costs. So let's take a look into these two positions, these two portions of the information. We can start with the base to organize. If we're thinking about the base, we mean down there where the squiggly line is. The base is at $8 per square meter. So let's call this base cost is going to be equal to, I'll write this as 8, again dropping units until the last problem part, the conclusion. $8 per square meter, which means it's $8 times the area. The area is going to be width times length, so that means it's going to be 8 times x for the width times 3x for the length. So take all that together, that's a 24x squared. So really all we did is we took the area of the base, 3x squared, multiply it by the cost per square meter times 8. There's the times 8 there. And now we have 24x squared dollars if you threw in the unit for the base cost. Now we're going to work into the side costs, but there's two kinds of sides. So let's continue to organize in the same way. There's the front and back face. So let's say it that way. Front slash back cost. Let me put down a squiggly line to just say what we mean. Here's the front face. Here's the back face. So we want to find cost for those. And we do this in the same exact way. The material cost is $5. So we can put down $5 first. But the thing that's new on this one is that there's two sides, right? The front face, the back face. So we have to go times 2. And then times area. So that's what the organization would look like for that portion there. So this becomes 10 times the area. The area is the width times the height. So here's width and height. So we can take a width x times a height. We call the height y. So it's 10xy. But you know what? This is a good time to use that as a substitution. We also know that y is 4x power negative 2. We can plug that in our next step. So the front back cost is now equal to 10x times, here's a substitution in for the variable y right here from our work on the left, 4x power negative 2. So that's kind of cleaning itself up. That looks a little bit better. If we take that to combine them, we get 40 x power negative 1 altogether. 4 by 10 giving the 40, combining x times x squared for x power negative 1. So that's the front and back panel. We need the left right panel, and then we're through with it. Any questions at all with the analysis at the moment? Okay, let me reset the squiggly lines. Now we're looking into the other faces. There's the face to the right, that panel. There's the face to the left, that panel there. We need to do the same thing. Material cost for all sides, it's saying, is $5. So this analysis is very, very similar on the next one. Let's call this left slash right cost for the left panel, the right panel at $5 per square meter. So we take 5, but as our sketch indicates, there are 2 panels, so we have to multiply by times 2 again, times the area. So similarly done on this one. This is going to be 10 times. Now we need the area. The area is the length times the height. So that's just going to be 3x times y. So altogether, this becomes 30 xy. But there's lots of parallelism in how this one's going. We need to eliminate y. Our methods are single variable calculus. To optimize this, y has to be substituted out. So we go back here and say that this is equal to 30x times substitution in for y, once again, 4x power negative 2. So that will give us 30 times 4, so 120 x power negative 1. So now we have the total cost analysis in parts. We can put them all together. And once we put them all together, we have this part. The cost function is ready to be built. You can call it whatever you like. It could be called f of x, g of x if you're feeling like g needs more attention. I'll call it c just to match up the instructions verbatim. So the total cost, c of x, is going to be equal to go to these three pieces, 24x squared, 40x power negative 1, 120x power negative 1. Add them all together. And as a bonus, we have like terms. So we can now say that C of x is 24x squared plus 160x power negative 1. So we did this step. Cost function is down. That is a lot of work, but you know it's no problem if you practice the one that we did in the lecture notes. I think there's something similar like this in the optimization section as well. Practice this problem again. If you want a clean diagram, a clean set of notes, you can go here. The sample final exam is also contained in the blank lecture notes. So you can just print this out and practice it again if you like as a clean sheet. Now, once we get here, we need the critical number of our cost function, but that's just redoing what we did in the prior example. So that's where the methods are starting to become basically the same. Next step is compute the derivative C prime. This time the derivative is straightforward, no chain rule. We're going to get 48x minus 160 x to the power negative 2. Once we have the critical number, we set it to 0 and solve it. Okay, there it is, set to 0. And solving something like this set to 0, we explore two different strategies. One strategy is just right where this equation stands, multiply the left side and the right side by x power negative 2. I think the strategy everyone preferred a little bit more was add this to the right-hand side. So you could rewrite it as 48x is 160 x power negative 2. Then whether you undo the negative exponent, divide by x squared or not, the next step is pretty much the same. Multiply by x squared here, multiply by x squared here. That is effectively clearing the denominator. It's getting x on one side because x power negative 2 times x squared is x power to 0, which is a 1. So now you have on the left side 48 x cubed equals 160 with a clean cancellation here. It's a good time to now go back to the calculator. Oh, sorry, it looks like I missed a couple chats. Naomi says, divide by x. Yes, if you divide by x here, you'd have x power negative 3, but that means you have x in a denominator, so you'd want to then multiply by x cubed to bring it back up into the numerator. So you could go that route to get x on one side, but we also need it as a positive exponent up in the numerator as well. Other questions at the moment? Okay, continuing on to the next step, let's divide 160 by 48. We get 3 repeating. That's kind of interesting. Let's said not to round till any intermediate computations. You know, I think I put that there just for the sake of making sure we got a pretty accurate answer. I wouldn't be too opposed if you round that to an appropriate place. Your algebra is going to be easy to read, the calculus will, and I'm going to see your minimum value be pretty close. And most calculators, you could click a button and just get that it reduces to that nice value, 10/3, but it feels like I'm cheating a little bit. So no harm if you also just go along these lines. Say x cubed equals 160 over 48. You can divide this by, say, 8. 8 would go in the numerator 20 times. 8 would go in the denominator 6 times. 8 is 48, so 6 times. Then you can divide by 2. 2 goes into the numerator 10 times and into the denominator 3 times. But again, if you did approximate that to say like 3.333, something like that, I wouldn't be too put off by it. So x cubed is 10 power 3. That means finally x, if we take the cube sides, is 10 thirds to the 1/3 power. So finally, we've got it, folks. Putting this all together, that's our result. 3 1/3. Yeah, you could write that as a mixed number, 3 1/3 as well. Absolutely. Other questions so far? Okay, well, that was this part. We've got the critical number of C. So let's just indicate that this is the critical number of the cost function. You don't necessarily have to say that, but I think that helps organize our thoughts. So we have a cost function here. And one thing we could say is, don't forget that it has a domain. X is bigger than 0. Haley says, I just remembered that if the decimal is 0.3, say repeating, it's a third, and 0.6 repeating is 2/3. Yeah, absolutely. So also you could say 3 would go into the 10 3 times. That would be the 3 part with the remainder 1. So that would be the 1/3 for the 0.3 repeating. So yeah, a lot of different ways to look at that. Other questions so far? Okay, now instructions did say to do something specific, I think. Let me see. No, not really. Oh, yeah, it's down here. Find the absolute minimum cost and use the second derivative test to prove that in fact it's an absolute minimum. That's not a strict requirement either, but I did put this on the real exam. If the first derivative test is a little bit more optimal, I would have said that. On this one, the second derivative test is the more optimal test to use. So that's why I put it in the instructions here. If you are dead set on the first derivative test, you can use it. It's probably just more steps. Definitely more steps on this problem. So how does the second derivative test go? It's actually quite nice. If you differentiate this function, sorry, we have to look at the right spot. Let me kind of highlight it. If you differentiate that function again to get the second derivative, then all we have to do is justify why is the second derivative always positive. Always positive in the second derivative test means an absolute minimum when there's exactly one critical number, just like we have. So differentiate it again, you'll get 48. This will be plus 360. X to the power of -3. And because x can only ever be positive, this is absolutely a positive number, always larger than 48. So this is bigger than 0 for all x bigger than 0. So if we take a moment to consult our handout on the real final exam, here's the test that we're using. Let's bake it into the problem right here. And this gives us good information on what our next conclusion is going to be. Haley says 320. Yeah, absolutely. Thanks for spotting that. I don't know where the 60 came from. If we differentiate that, double that, would be 320 altogether. Thanks for spotting that. To both Naomi and Haley. Other questions or comments at the moment? Okay, well, let's look at what this test says. First derivative test, that's the wrong one. Let's try again. We want the second derivative test. So that's this one right here. Makes sense that it'd be on the notes in the second spot. There we go. Okay, first, we have to have the second derivative is continuous near our critical number C. Definitely, that's continuous function everywhere except for 0. It says if f prime at C is 0, that's what we were doing here. Here's the C prime. We solved to get 0, and that's the critical number, 10 thirds to the power 1/3. And if the second derivative is always positive at that critical number, we have a local minimum, but we're jumping to this part. If the second derivative is bigger than 0 for all x in the domain of our function. That's the domain, all positive numbers. And yeah, in that same domain, it is always positive. You get an absolute minimum. So that's what our conclusion is going to be now. The absolute minimum take this function. We want to find the absolute minimum cost. So we're going to go C at, plug in the critical number, 10 thirds to the power 1/3. It's going back inside the original cost function. So kind of looks ugly at first, but let's put it in. 24 in place of x, 10 thirds to the power 1/3 squared. So I have stacked parentheses on there to indicate it correctly, plus 160. 10 thirds to power 1/3 to the power of -1. So there it all is. That is our absolute minimum cost. We need to plug it into a calculator, so taking one step on the exponents actually helps out with the calculator for accuracy. So I'm going to say the cost at 10 thirds to the power of 1/3, recall that's in terms of meters for our diagram, is going to be 24 times 2 will multiply the 1/3, so it's going to be 10 thirds to the power 2/3 plus 160. -1 multiplies 1/3, so it's going to be 10 thirds to the power of -1/3. Now we can plug it into the calculator, get a value to nearest cent. So to the nearest cent, this is 24 10 thirds to the value exponent 2/3. We're up to $53, but that's not the whole story, plus 160 of 10 thirds to the power of -1/3 gets us $160.66. Again, this is weird because this is a gigantic container. But as far as the math goes, that would be what the conclusion is. So we have to jump through a lot of hoops on this one. We had to build the function. I think that's the longest part of the process. Differentiate it, get a critical number. Second derivative test just proves that that critical number does in fact give the absolute minimum. Then now that we know that, we take the same critical number, plug it back into the function. So it's like a big circle of values that ends up at a cost analysis of $160.66 at minimum. The dimensions off of 10 thirds and the cost guaranteed will go up. Well, 10 thirds to a power of 1/3, kind of an interesting dimension. Well, we did it, folks. That's our last run at this optimization problem. Any questions at all at any of the stages of the process? Okay, well, we're materials on this. After this, chapter 4 was effectively basically over, except we had some information on antiderivatives that led us into the fundamental theorem of calculus. So that's what we're going to do for the last problems. Let's start taking a look into antiderivatives for the last segment of our review. The review for antiderivative is we're building a function. We usually call it uppercase f of x, or if you like, we could call it the integral of f of x dx. This is what we were calling it in section 4.3. So I'll leave it be up to you. You can do it exactly as we did in 4.7, call it an f of x function like this, or write it as an indefinite integral as we did in section 5.3, the last part of the notes that we covered. Really, it's just a matter of notation. I'll do it in both ways. Let's do the common notation section 4.7 for part A, and I'll use the fancy new notation for part B so that we can get two different takes on this. And again, you're welcome to use any notation you'd like. So the way we usually color code these is we had a function that was in green, the original function f of x. We said there's a lot of stuff that we want to have working for us on paper. We're going to use the reverse of the power rule, so that base needs to be in the numerator to effectively use it without getting mixed up in directionalities of which way the exponent is going, up or down. So let's rewrite f of x is 3x squared minus e to the x plus 5 plus the natural log of 7. Once we have that, because this was some of the material that was right at the end, I don't think that on, say, exam 3, I put in a lot of material along these lines on the review, or excuse me, the notes for the final exam. So this information is quite helpful, whether you're using one notation or the other. Here is the reversal of the power rule, for example. We'll use it on this term, and the antiderivative of e to the x is also indicated here. It also has a reminder that we need a constant of integration. We're just going to write 1, but there's 1 per formula. So citing those formulas, we can say the antiderivative f of x is, on a term-by-term basis, the process is, whatever your exponent was, it goes up by 1. So this cubed, we take the new exponent and we divide into it. But that means 3 is dividing that 3 in green that's in front, so it's just gone. Different. You do in fact get 3x squared. So that's 1 term down. And then it's rinse and repeat. Whether you're differentiating, taking antiderivatives, it's nice when things are being added and subtracted. If it's an e to the x, its antiderivative is just minus e to the x, and it's done right at that step. This one we want to be a little bit more careful with. Put in a little bit of space. The rule says here, power goes up by 1. So from a -5, we go to a -4. Then from this spot, it's telling us divide by that -4. I'll write it like this. -1/4. Or you could go plus 1 over -4 if you prefer. So the last one is absolutely the trickiest one on the list. Anyone recall what happens when we take the antiderivative of a constant, natural log 7? Absolutely, Haley. All we do is, just as you said, tack on that x. So this is going to be plus natural log 7 times x. And it looks weird because of the natural log function, but the thought is, if you had a y equals 7 times x working by analogy, and you differentiate that, y prime is just 7. Think of the natural log 7 as it's now an irrational number, but it's just like a 7 times x. Differentiate this whole thing, and x vanishes. You get back just the natural log of 7, much like with this analogy here. Then the one thing we have to remember is this is implied that we're finding the most general antiderivative possible. So we add the constant of integration, like that c's that we see here in the formulas. So that's 1 down. If you have extra time on the exam, not a bad idea to go into the margin and differentiate the whole thing. Or if you're mentally differentiating every time you put down a term after term, then you might feel confident right at this stage. Yeah, that looks about right. Differentiating all of these terms gives us back the original f of x function. Well, we'll do it again and then take a look into the fundamental theorem of calculus. Any questions or comments at all, folks, on this one? Naomi says, would you be able to go over differentiating logarithmic functions more when it's supposed to be a 1 over x or 1 over natural log b, and when it's supposed to be x prime divided by x, x prime over natural log b? Is that when you use the chain rule? Yeah, absolutely. And yeah, I can put down a problem just like that. Let's take a look. So for this question here, let's take a look into just a category of different functions. One function could be f of x equals natural log x. We've seen that already in the notes, but let's put it here just for the sake of an overall comparison. Another one could be, say, g of x equals maybe it's something like 7 log base 8 of x. And then to complete our category of different functions, different adventures to get into, let's say for another one, it's h of x equals, it could be something like, how about log base 11 of 7x squared minus 8x plus 2. And then final one, I'm running out of letters, h, I, a, b, c, d, f, g, h. I guess the next function's I, but that just looks funny. Let's instead call it a different f, uppercase F. And let's let this one be something like 18x natural log. And how about, let's think of a good one here. You know, this one's kind of fun just like that. That would be a decent challenge. So here's 4 different logarithmic functions. They all have their different issues. Also, take a look into your exam 3. Redifferentiate those problems, and that gives you another good take on each one of these kinds of concepts. For the first one, this one's the warm-up. If you differentiate the natural log of x, then f prime at x is a 1 over x. On this one, the rules get a little bit more involved. It's a constant multiple rule, but that 7 doesn't really cause any problems. X still goes into the denominator, but here's a related formula that must be memorized for the exam, that the derivative with respect to x of log base b of x is 1 over x natural log of b. And while we're stating formulas, another formula that we need for the exam, it's kind of contained here. You just have to put the natural log into the numerator position, but let's still state it nonetheless. As a derivative formula, not an antiderivative formula, the derivative with respect to x of b to the power of x is b to the power of x times the natural log of b. So those are 2 pairs of formulas that go together. So if we're going back to the g of x function and use these formulas, g prime at x is going to be 7 stays where it is. It's going to now be divided by x. So x goes down below, but it's not a natural logarithm. If it's log base 8, that's where this part gets involved. So we throw in natural log 8. So that's 2 formulas so far. More challenging, the chain rule, like you were mentioning. And this one up to the right of it is going to be the product rule. But any questions with these so far? Okay, running through these, here's what they're going to look like. Let's maybe color code this one carefully because it is a chain rule. Naomi says, so for that problem, we wouldn't take the derivative of x, put it into the denominator if it was like a 6x instead of just x. Are you referring to, say, this last one we did here? It was a 6x in this position, it'd be more similar to the 18x that we're going to do on this one right here. So yeah, if there was a 6x right here, we would have to use the product. If it was a 6x on the inside, I think that's what you're referring to, inside the logarithmic function, a 6x here would put a 6x down below, but then you would have to multiply by 6. That one would involve a chain rule, which is effectively what we're doing on this one, but this one's just a little bit more built up. So even if it looked like this one would still be the chain rule in that kind of format. Does that make sense for that question there? Yeah, absolutely. And we might as well do that one. That one kind of builds on the chain rule. Let's call h of x log base 23, because we've never done a log base 23. We might as well make today be the one and only day we get a chance to do it. How about something like what we had? I forgot what it was, but we can make it just as interesting as it was before. Segment x cubed plus 12x squared minus 11. So let's go for both of these. So in the chain rule process, first we differentiate log base 11 at x. Then we differentiate 7 to the power of x. So this would be the inner function. This would be the outer function. The 1 and 2 tell us the order to do the derivatives. So on that version, h prime of x is going to be equal to, here, I'm going to leave the numerator break. Actually, it wouldn't hurt to take an extra step. Let's take an extra step on this one and write out this way. Okay, so there's our derivative for the first derivative of base 11. Nomi says, so if the base is raised to anything other than just x, we use the chain rule. When you refer to the base, are you meaning the base of the logarithm, or are you meaning the function inside the logarithm? So as far as the base goes, yes, so 11 is the base here. And if the base is raised to when you say raised to, I think that's where you're meaning what's inside here. Raised to anything other than x, we use the chain rule. Yeah, absolutely. However, if you swap in any function, whether it's a natural log, a square root, x to the power of 2/3, if you put in place of x anything other than x, it's automatically a chain rule, whether it's a logarithm or otherwise. But logarithms and exponentials tend to be the tricky ones. Does that make sense with the answer there? Okay, let's try this out then. So what I did first with what I've written here is, this is just the derivative of log base 11. This part's right here. That part where we're going times the derivative, that's the chain rule portion. Then we take the inner function, 7x and 7x. And maybe to build on that comment that you're asking about, Naomi, suppose you did use the chain rule on this one. If you multiply by the derivative of x, you would get a 1. And so in a really real sense, the chain rule is always used. It just so happens if the derivative is 1, we ignore it. The derivative of that is not 1, and so this is the only reason we're using the chain rule. And that's a good way to think of why is the chain rule involved. It's because the derivative of the input is not 1 any longer. It's something other than 1. So when we go through this, finally, h prime at x is going to be, let's copy in the 7x that we dropped down below. Natural log of 11. Derivative of 7x here is a 7. Gives us a cancel over 7. So this becomes 1 over just x, natural log 11. So we have 2 more to take a look into, but any questions with that one? Okay, for this next one, I recall that whenever it was a product rule or a quotient rule in exam 3, these were pretty tricky as well. So let's take our time with this one. This one's going to be the good old product rule. I'll organize the product by taking that entire thing, 18x, as the first factor. Natural log x is the second factor. So if we go to differentiate this, we say f prime of x is going to be 18x prime times natural log x plus 18x times natural log x prime. And as far as the color code goes, it's the first function differentiated, multiplied by the second function copied, Then add first function copied, multiplied by the second function differentiated. Once you have that down on paper, it's just go right through the last derivatives. F prime at x is now, derivative of 18x is 18 times natural log x. So that's what happened with that derivative there, plus 18x times the derivative of natural log x is a 1 over x, which means this one has the opportunity to simplify. This turns into just 18 natural log x plus 18. So this one's tricky. It's not 18 times 1 over x. If you have any function times any other function where there's a variable involved, x on the first part, x on the second part, it's automatically a product rule. So that's a pretty good roundup so far. We had kind of the starter problems where the formulas where we had to pay real close attention to. More built-up problems where chain rule, product rule gets involved. And in view of everything we've done, this one is just another chain rule, same exact kind of process. So that's going to be the inner function, just like we organized before. Excuse me, I said that backwards. That's the outer function. The inner one is that one, the one in green. I should probably write this in for emphasis. That's function 2, inner. And this is function 1, the outer. So differentiating this one, first we're following the rule that you see right here. Let me continue to highlight those natural logs to show where they got involved. Differentiate log base 23, and I mean, it sounds impressive, but it's the same stuff as before. 1 over whatever the input is going down into the denominator multiplied by the natural log of 23. So that whole structure that I put down in blue is the derivative of log base 23 of x. X is not there. We put in a placeholder because we have something other than just x going in. So here's where we go, multiply by the derivative of whatever the inner function is, 7x cubed plus 12x power -2 minus 11, copies in both spots. Finally, we're just going to differentiate this, multiply it in, push it up into the numerator when we multiply the fraction, and this is our result. Cubed plus 12x squared minus 11 times natural log 23. And then derivative of this one, we're basically there. Power rule, sum rule, all those rules, constant multiple rule, and the constant 21, x squared plus 24 x. So that was our good rundown on rules with logarithms. They're definitely the trickier derivative section. Other questions or comments about these at the moment? Okay, well, we're nearly there. I think we have about enough time for 1 or 2 more problems. If you have other problems to suggest from anyone in the class, I'm thankful for your suggestions, Naomi. Don't hesitate to throw them out there. Otherwise, looks like we have one more antiderivative to take a look into before turning into fundamental theorem of calculus. And like I mentioned before, any problems that don't get finalized tonight, after I finalize all my grading on Friday, I'll be turning next to just getting these completely solved, uploaded back into Canvas. So here's our next one going in order. Here's our g of x function. We want an antiderivative on this one. But this one is definitely pretty tricky to work with. The trouble with differentiating is you cannot differentiate that by differentiating x, 2x minus 5, x squared plus 1, and then divide by the derivative of x squared. This one would be a nasty quotient rule with a product rule to do the total derivative in that format. So whether you're differentiating or finding the antiderivative, it's a really good idea to take these and work some algebra on it first. We want to simplify that down as much as feasibly possible by first expanding out the numerator. So here's how it's going to go. FOIL that groups 2x minus 5, x squared plus 1 to get 2x cubed plus 2x minus 5x squared minus 5. Then expand further by distributing x into that group. Numerator is 2x power 4, slightly nicer going in order. So I'm going to multiply that by x, minus 5x cubed. Then come back to this term, plus 2x squared. Now over to this term, so kind of zigzag a little bit, minus 5x. All over x squared. And you could have formatted this different because now what we're going to do is just take every term. I'll write it in for the notes just to emphasize. Every term now gets divided by x squared. So at this stage, we're nearly done. Use rules of laws for exponents to get 24x squared on the first term, minus 5x on the second term. Clean cancellation here, just a plus 2. And here, this is the dangerous one. When we simplified this one, this is the one and only time where we need to be really, really on the lookout for a 1 over x that ever occurs, because the antiderivative there does not follow this process whatsoever. That's the natural log of absolute value of x. Oh, let me double check. Yeah, good question. I'm not sure where 24 came from. I probably just did a micro sleep and wrote in the exponent as well. That should have just been a 2 here. And like a game of telephone, it kept on getting copied down. So 2 both here and here. Thanks for spotting those. Then next, with this one, let's rewrite it as minus 5 times 1 over x. Out of safety first on this one. So there's our g of x function. When it says come up with the antiderivative, we can view it in this way. An antiderivative is just an indefinite integral. So in other words, the antiderivative as an indefinite integral, no lower limit or upper limit of integration, so no numbers there, there's no interval we're integrating over. We just take g of x dx and start using the power rule, this one down here, term by term, until we get to the exception case, the 1 over x. So in the first one, we had a 2, power next goes up by 3, and then we divide by that 3. Differentiate that, the 3 comes down, cancels, and you just get 2x thing. So rinse and repeat. The exponent here is a 1, but it goes up to a 2. So it becomes negative 5, x power 2, then immediately divide by that 2. Here it's a constant, so just like we did prior in the notes, I think it was like natural log 6 or something. Any constant whatsoever, tack on an x. Because the derivative of 2x is in fact that 2. Here, a constant multiple rule works for antiderivatives as well. So we can go minus 5, do the antiderivative of 1 over x, which is natural log. It must be an absolute value of x to make the antiderivative as general as possible. Then add the constant of integration c. So that's our full antiderivative, whether you called it an f of x, or you use the indefinite integral symbolism, like we see down here in the formulas, it's the exact thing. Well, we're on our last minute, so this will be our stopping point for the night. But any last thoughts or questions before we call it a day? Okay, well, thanks everyone for all your hard work this semester. Congratulations on getting through the entire semester. It is a feat to get through 15 weeks of calculus in any calculus class whatsoever. And last takeaway is I'm going to be working on grading as my first step when I go to on Friday. After I complete grading for all my classes, I'm going to start doing these kind of documents, finalizing the solutions. If you have any questions while you're studying, don't hesitate to email. We won't have class at all next week, except for the in-person section. We're meeting on Tuesday from 5:30 to 7:30 p.m. For the online section, if you haven't done so, please schedule your final exam as soon as possible. But otherwise, if you have any questions, don't hesitate to email at any point, even during finals week. I'll be happy to engage with you. But have a great night, folks. Try not to. We're nearly through with all of it. You bet. Thanks. Have a good one, folks.